Hello! Welcome to All Essays. Reach your academic heights. My name is Julie and I will be your instructor as we read through 3.2 Data Acquired and Source Change Detection in Land Use and Land Cover using Remote Sensing Data and GIS. The article source is embedded in the video description below. Feel free to read along. Please note that you can get a custom, plagiarism-free essay for as little as $10 a page at All Essays. The link is in the description. Chapter 1 Introduction 1.1 Background to the study. Studies have shown that there remains only few landscapes on the Earth that are still in their natural state. Due to anthropogenic activities, the Earth's surface is being significantly altered in some manner, and man's presence on the Earth and his use of land has had a profound effect upon the natural environment, thus resulting into an observable pattern in the land-use land cover over time. The land-use land cover pattern of a region is an outcome of natural and socio-economic factors and their utilization by man in time and space. Land is becoming a scarce resource due to immense agricultural and demographic pressure. Hence, information on land use/land cover and possibilities for their optimal use is essential for the selection, planning and implementation of land use schemes to meet the increasing demands for basic human needs and welfare. This information also assists in monitoring the dynamics of land use resulting out of changing demands of increasing population. Land use and land cover change has become a central component in current strategies for managing natural resources and monitoring environmental changes. The advancement in the concept of vegetation mapping has greatly increased research on land use land cover change, thus providing an accurate evaluation of the spread and health of the world's forest, grassland, and agricultural resources has become an important priority. Viewing the Earth from space is now crucial to the understanding of the influence of man's activities on its natural resource base over time. In situations of rapid and often unrecorded land use change, observations of the Earth from space provide objective information of human utilization of the landscape. Over the past years, data from Earth sensing satellites has become vital in mapping the Earth's features and infrastructures, managing natural resources and studying environmental change. Remote sensing, RS, and Geographic Information System, GIS, are now providing new tools for advanced ecosystem management. The collection of remotely sensed data facilitates the synaptic analyses of Earth, system function, patterning, and change at local, regional and global scales over time. Such data also provide an important link between intensive, localized ecological research and regional, national and international conservation and management of biological diversity, Wilkie and Finn, 1996. Therefore, attempt will be made in this study to map out the status of land use land cover of Ilorin between 1972 and 2001 with a view to detecting the land consumption rate and the changes that has taken place in this status, particularly in the built-up land, so as to predict possible changes that might take place in this status in the next 14 years using both Geographic Information System and remote sensing data. 1.2 Statement of the problem. Ilorin, the Kwara state capital, has witnessed remarkable expansion, growth and developmental activities such as building, road construction, deforestation and many other anthropogenic activities since its inception in 1967, just like many other state capitals in Nigeria. This has therefore resulted in increased land consumption and the modification and alterations in the status of her land use land cover over time without any detailed and comprehensive attempt, as provided by remote sensing data and GIS, to evaluate this status as it changes over time with a view to detecting the land consumption rate and also make attempt to predict same and the possible changes that may occur in the status so that planners can have a basic tool for planning. It is therefore necessary for a study such as this to be carried out if Ilorin will avoid the associated problems of a growing and expanding city like many others in the world. 1.3 Justification for the study. Indeed, attempt has been made to document the growth of Ilorin in the past, but that from an aerial photography. Olorunfemi, 1983. In recent times, The dynamics of land use, land cover, and particularly settlement expansion in the area requires a more powerful and sophisticated system such as GIS and remote sensing data, which provides a general extensive synoptic coverage of large areas than area photography. 1.4 Aim and Objectives. 1.4.1 Aim. The aim of this study is to produce a land use land cover map of Ilorin at different epochs in order to detect the changes that have taken place, particularly in the built-up land, and subsequently predict likely changes that might take place in the same over a given period. 1.4.2 Objectives. The following specific objectives will be pursued in order to achieve the aim above. To create a land use land cover classification scheme, to determine the trend, nature, rate, location and magnitude of land use land cover change. To forecast the future pattern of land use land cover in the area. To generate data on land consumption rate and land absorption coefficient, since more emphasis is placed on built-up land. To evaluate the socio-economic implications of predicted change. 1.5 The study area. The study area, Ilorin, is the capital of Kwara State. It is located on latitude 8031N and 4035E with an area of about 100 kilometers square. Kwara State Diary 1997. Being situated in the transitional zone between the forest and the savanna region of Nigeria, that is the north and the west coastal region, it therefore serves as a melting point between the northern and southern culture. Oyebonji, 1993. Her geology consists of Precambrian basement complex with an elevation which ranges between 273 m to 333 m in the west and 200 m to 364 m in the east. The landscape of the region, Ilorin, is relatively flat. This means it is located on a plain and is crested by two large rivers. The river Asa and Oin, which flows in north-south direction, divides the plain into two. Western and eastern part, Oyebonji, 1993. The climate is humid tropical type and is characterized by wet and dry seasons. Ilorin Atlas 1981. The wet season begins towards the end of March and ends in October. A dry season in the town begins with the onset of tropical continental air mass, commonly referred to as harmattan. This wind is usually predominant between the months of November and February. Ilorin 2002. The temperature is uniformly high throughout the year. The mean monthly temperature of the town for the period of 1991 to 2000 varies between 250 C and 29.50 C, with the month of March having about 300 C. Ilorin falls into the southern savanna zone. This zone is a transition between the high forest in the southern part of the country and the far north with woodland properties. Osoba, 1980. Her vegetation is characterized by scattered tall tree shrubs of between the height of 10 and 12 feet. Oregon in 1993 described the vegetation to be predominantly covered by derived savanna found in east and west and are noted for the dry lowland rainforest vegetal cover. As noted by Oregon in 1983, Ilorin is one of the fastest growing urban centers in Nigeria. Her rate of population growth is much higher than for other cities in the country. Oregon, 1983. Ilorin City has grown in both population and a real extent at a fast pace since 1967. Oregon, 1983. The In-Plan Group, 1977, puts the population at 400,000, which made it then the sixth largest town in Nigeria. The town had a population of 40,990 in 1952 and 208,546 in 1963 and was estimated as 474,835 in 1982, Oregon, 1983. In 1984, the population was 480,000, Oregon, 1985. This trend in population growth rate shows a rapid growth in population. The growth rate between 1952 and 1963 according to Oyebonji, 1983 is put at 16.0, which is higher than other cities in the country. The population as estimated by the 1991 population census was put at 570,000. 1.6 Definition of terms. Remote sensing can be defined as any process whereby information is gathered about an object, area or phenomenon without being in contact with it. Given this rather general definition, the term has come to be associated more specifically with the gauging of interactions between Earth's surface materials and electromagnetic energy. ITRESI 32 Guide to GIS and Image Processing, Volume 1. Geographic Information System, a computer-assisted system for the acquisition, storage, analysis and display of geographic data. A9AYTZ355N 32 Guide to GIS and Image Processing, Volume 1. Land use. This is the manner in which human beings employ the land and its resources. Land cover implies the physical or natural state of the Earth's surface. Chapter 2.1 Literature Review. According to Meyer, 1999, every parcel of land on the Earth's surface is unique in the cover it possesses. Land use and land cover are distinct yet closely linked characteristics of the Earth's surface. The use to which we put land could be grazing, agriculture, urban development, logging, and mining among many others. While land cover categories could be cropland, forest, wetland, pasture, roads, urban areas among others. The term land cover originally referred to the kind and state of vegetation, such as forest or grass cover, but it has broadened in subsequent usage to include other things such as human structures, soil type, biodiversity, surface and groundwater. Meyer, 1995. Land use affects land cover and changes in land cover affect land use. A change in either, however, is not necessarily the product of the other. Changes in land cover by land use do not necessarily imply degradation of the land. However, many shifting land use patterns driven by a variety of social causes result in land cover changes that affects biodiversity, water and radiation budgets, trace gas emissions and other processes that come together to affect climate and biosphere. Riepsame, Meyer, and Turner, 1994. Land cover can be altered by forces other than anthropogenic. Natural events such as weather, flooding, fire, climate fluctuations, and ecosystem dynamics may also initiate modifications upon land cover. Globally, land cover today is altered principally by direct human use, by agriculture and livestock raising, forest harvesting and management, and urban and suburban construction and development. There are also incidental impacts on land cover from other human activities such as forest and lakes damaged by acid rain from fossil fuel combustion and crops near cities damaged by tropospheric ozone resulting from automobile exhaust. Meyer, 1995. Hence, in order to use land optimally, it is not only necessary to have the information on existing land use land cover but also the capability to monitor the dynamics of land use resulting out of both changing demands of increasing population and forces of nature acting to shape the landscape. Conventional ground methods of land use mapping are labor-intensive, time-consuming and are done relatively infrequently. These maps soon become outdated with the passage of time, particularly in a rapid-changing environment. In fact, according to Oler and Femi, 1983, monitoring changes and time series analysis is quite difficult with traditional method of surveying. In recent years, satellite remote sensing techniques have been developed, which have proved to be of immense value for preparing accurate land use land cover maps and monitoring changes at regular intervals of time. In case of inaccessible region, this technique is perhaps the only method of obtaining the required data on a cost and time-effective basis. A remote sensing device records response which is based on many characteristics of the land surface, including natural and artificial cover. An interpreter uses the element of tone, texture, pattern, shape, size, shadow, site and association to derive information about land cover. The generation of remotely sensed data images by various types of sensor flown aboard different platforms at varying heights above the terrain and at different times of the day and the year does not lead to a simple classification system. It is often believed that no single classification could be used with all types of imagery and all scales. To date, the most successful attempt in developing a general-purpose classification scheme compatible with remote sensing data has been by Anderson et al., which is also referred to as USGS classification scheme. Other classification schemes available for use with remotely sensed data are basically modification of the above classification scheme. Ever since the launch of the first remote sensing satellite, Landsat-1, in 1972, land use land cover studies were carried out on different scales for different users. For instance, wasteland mapping of India was carried out on 1 million scales by an RSA using 1980-82 Landsat multispectral scanner data. About 16.2% of wastelands were estimated based on the study. A9AY, and Ranking LQY in 1999 noted that information about changes necessary for updating land cover maps and the management of natural resources. The information may be attained by visiting sites on the ground and/or extracting it from remotely sensed data. Change detection is the process of identifying differences in the state of an object or phenomenon by observing it at different times. Singh, 1989. Change detection is an important process in monitoring and managing natural resources and urban development because it provides quantitative analysis of the spatial distribution of the population of interest. MacLeod and Congation, 1998, lists 4 aspects of change detection which are important when monitoring natural resources. I. Detecting the changes that have occurred. E. Identifying the nature of the change. E. Measuring the area extent of the change. F. Assessing the spatial pattern of the change. The basis of using remote sensing data for change detection is that changes in land cover result in changes in radiance values which can be remotely sensed. Techniques to perform change detection with satellite imagery have become numerous as a result of increasing versatility in manipulating digital data and increasing computer power. A wide variety of digital change detection techniques have been developed over the last 2 decades. Singh, 1989, and Koppen and Bauer, 1996, summarize 11 different change detection algorithms that were found to be documented in the literature by 1995. These include 1. Monotemporal change delineation. 2. Delta or post-classification comparisons. 3. Multidimensional temporal feature space analysis. 4. Composite analysis. 5. Image differencing. 6. Multitemporal linear data transformation. 7. Change vector analysis. 8. Image regression. 9. Multitemporal biomass index. 10. Background subtraction. 11. Image ratioing. In some instances, land cover change may result in environmental, social and economic impacts of greater damage than benefit to the area. Moshin, 1999. Therefore, data on land use change are of great importance to planners in monitoring the consequences of land use change on the area. Such data are of value to resources management and agencies that plan and assess land use patterns and in modeling and predicting future changes. Shawsheng and Cuddio, 1994, investigated the advantages of remote sensing techniques in relation to field surveys in providing a regional description of vegetation cover. The results of their research were used to produce 4 vegetation cover maps that provided new information on spatial and temporal distributions of vegetation in this area and allowed regional quantitative assessment of the vegetation cover. Arvind C. Pandey and M.S. Nathawat, 2006, carried out a study on land cover mapping of Panchkula, Ambala and Yamunanagar districts, Haryana state in India. They observed that the heterogeneous climate and physiographic conditions in these districts has resulted in the development of different land cover in these districts. An evaluation by digital analysis of satellite data indicates that majority of areas in these districts are used for agricultural purpose. The hilly regions exhibit fair development of reserve forests. It is inferred that land cover pattern in the area are generally controlled by climatic conditions, groundwater potential and a host of other factors. It has been noted over time through series of studies that Landsat thematic mapper is adequate for general extensive synoptic coverage of large areas. As a result, this reduces the need for expensive and time-consuming ground surveys conducted for validation of data. Generally, satellite imagery is able to provide more frequent data collection on a regular basis, unlike aerial photographs which, although may provide more geometrically accurate maps, is limited in respect to its extent of coverage and expensive. Which means, it is not often used. In 1985, the U.S. Geological Survey carried out a research program to produce 250,000 scale land cover maps for Alaska using Landsat MSS data. Fitzpatrick, et al., 1987. The State of Maryland Health Resources Planning Commission also used Landsat TM data to create a land cover data set for inclusion in their Maryland Geographic Information (MAGI) database. All 7 TM bands were used to produce a 21 class land cover map, EOSAT 1992. Also, In 1992, the Georgia Department of Natural Resources completed mapping the entire state of Georgia to identify and quantify wetlands and other land cover types using Landsat Thematic Mapper Unregistered Trademark Data, ERDAS, 1992. The State of Southern Carolina Land Resources Conservation Commission developed a detailed land cover map composed of 19 classes from TM Data, EOSAT, 1994. This mapping effort employed multi-temporal imagery as well as multispectral data during classification. An analysis of land use and land cover changes using the combination of MSS Landsat and Land Use Map of Indonesia, Dimyati, 1995, reveals that land use land cover change were evaluated by using remote sensing to calculate the index of changes, which was done by the superimposition of land use land cover images of 1972, 1984 and land use maps of 1990. This was done to analyze the pattern of change in the area, which was rather difficult with the traditional method of surveying, as noted by Olorunfemi in 1983 when he was using aerial photographic approach to monitor urban land use in developing countries, with Ilorin in Nigeria as a case study. Daniel et al., 2002. In the comparison of land use land cover change detection methods, made use of 5 methods, viz. traditional post, classification, cross-tabulation, cross-correlation analysis, neural networks, knowledge-based expert systems, and image segmentation and object-oriented classification. A combination of direct T1 and T2 change detection as well as post-classification analysis was employed. 9 land-use land cover classes were selected for analysis. They observed that there are merits to each of the 5 methods examined, and that, at the point of their research, no single approach can solve the land use change detection problem. Also, Adeni and Amujola, 1999, in their land use land cover change evaluation in Sokoto, Rima Basin of Western Nigeria based on archival remote sensing and GIS techniques, used aerial photographs, Landsat MSS, spot access panchromatic image transparency and topographic map sheets to study changes in the 2 dams, Sokoto and Goronyo, between 1962 and 1986. The work revealed that land use land cover of both areas was unchanged before the construction, while settlement alone covered most part of the area. However, during the post-dam era, land use/land cover classes changed, but with settlement still remaining the largest. Chapter 3 Research Methodology 3.1 Introduction. The procedure adopted in this research work forms the basis for deriving statistics of land use dynamics and subsequently in the overall, the findings. 3.2 Data acquired and source for the study. Landsat satellite images of Kwara State were acquired for 3 epochs: 1972, 1986 and 2001. Both 1972 and 1986 were obtained from Global Land Cover Facility, GLCF, and Earth Science Data Interface, while that of 2001 was obtained from National Space Research and Development Agency in Abuja, NASRDA. 0 and both 2001 and 1986 images, a notable feature can be observed, which is the Assa Dam, which was not yet constructed as of 1972. It is also important to state that Ilorin and its environs, which were carved out using the local government boundary map and Nigerian administrative map, was also obtained from NASRDA. These were brought to Universal Transverse Marcator Projection in Zone 31. 1, 2, 3. Landsat image 2001-11-03 November 15, 1986 November 7, 1972 30M Unregistered Trademark 30M TM 80M TM NASRDA GLCF 4 Formiku Land Use Land Cover Vegetation Map 1995 1495, 389, View Scale, Formiku 5 Administrative and Local Government Map of Nigeria 2005 15,140,906, View Scale, NASRDA 6 Land Use and Infrastructure Map of Ilorin 1984 150, Ilorin Agricultural Development Project Table 3.1 Data Source 3.2.1 Georeferencing Properties of the images. The georeferencing properties of both 1986 and 2001 are the same, while image thinning was applied to the 1972 imagery, which has a resolution of 80M using a factor of 2 to modify its properties and resolution to conform to the other 2 as given below. Data type, RGB8 file type, binary columns, 535 rows, 552 referencing system, UTM-31 reference units, M-unit distance, 1 minimum x, 657,046.848,948 maximum x, 687,541.848,948 minimum y, 921,714.4032881 maximum y, 953,178.4032881 minutes value, 0. Max value, 215 display minimum, 0 display maximum, 215 image thinning was carried out through contract. Contract generalizes an image by reducing the number of rows and columns while simultaneously decreasing the cell resolution. Contraction may take place by pixel thinning or pixel aggregation with the contracting factors in X and Y being independently defined. With pixel thinning, every nth pixel is kept while the remaining is thrown away. 3.3 software used. Basically, 5 software were used for this project viz. A. ArcView 3.2 This was used for displaying and subsequent processing and enhancement of the image. It was also used for the carving out of island and region from the whole Quora state imagery using both the admin and local government maps. B. ArcGIS. This was also used to complement the display and processing of the data. C. A9AYTZ355N. This was used for the development of land-use land cover classes and subsequently for change detection analysis of the study area. D. Microsoft Word, was used basically for the presentation of the research. E. Microsoft Excel was used in producing the bar graph. 3.4 Development of a classification scheme based on the priori knowledge of the study area for over 20 years and a brief reconnaissance survey with additional information from previous research in the study area. A classification scheme was developed for the study area after Anderson et al. 1967. The classification scheme developed gives a rather broad classification where the land-use land cover was identified by a single digit. 1 farmland, 2 wasteland, 3 built-up land, 4 forest land, 5 water bodies. Table 3.2 Land-use land cover classification scheme. The classification scheme given in Table 3.2 is a modification of Anderson's in 1967. The definition of wasteland as used in this research work denotes land without scrub, sandy areas, dry grasses, rocky areas and other human-induced barren lands. 3.5 Limitation, S. In this study there was a major limitation as a result of resolution difference. Landsat image of 1972 was acquired with the multi-spectral scanner, MSS, which has a spatial resolution of 80 meters, whilst the images of 1986 and 2001 were acquired with Thematic Mapper unregistered trademark and Enhanced Thematic Mapper, ETM, respectively. These both have a spatial resolution of 30 meters. Although this limitation was corrected for through image thinning of the 1972, it still prevented its use for projecting into the future so as to have a consistent result. Apart from this, it produced an arbitrary classification of water body for the 1972 classification. 3.6 Methods of data analysis. 6 main methods of data analysis were adopted in this study. I. Calculation of the area in hectares of the resulting land-use land cover types for each study year and subsequently comparing the results. E. Markov chain and cellular automata analysis for predicting change. E. Overlay operations. IV. Image thinning. V. Maximum likelihood classification. Vi. Land consumption rate and absorption coefficient. The first 3 methods above were used for identifying change in the land use types. Therefore, they have been combined in this study. The comparison of the land-use land cover statistics assisted in identifying the percentage change, trend and rate of change between 1972 and 2001. In achieving this, the first task was to develop a table showing the area in hectares and the percentage change for each year, 1972, 1986 and 2001, measured against each land-use land cover type. Percentage change to determine the trend of change can then be calculated by dividing observed change by sum of changes multiplied by 100. Trend, percentage change equals observed change 100 sum of change in obtaining annual rate of change. The percentage change is divided by 100 and multiplied by the number of study year 1972 to 1986, 14 years, 1986 to 2001, 15 years, Going by the second method, Markov chain analysis and cellular automata analysis, Markov chain analysis is a convenient tool for modeling land use change when changes and processes in the landscape are difficult to describe. A Markovian process is one in which the future state of a system can be modeled purely on the basis of the immediately preceding state. Markovian chain analysis will describe land use change from one period to another and use this as the basis to project future changes. This is achieved by developing a transition probability matrix of land use change from time 1 to time 2, which shows the nature of change while still serving as the basis for projecting to a later time period. The transition probability may be accurate on a per-category basis, but there is no knowledge of the spatial distribution of occurrences within each land use category. Hence, cellular automata, CA, was used to add spatial character to the model. CA Markov uses the output from the Markov chain analysis, particularly transition area file, to apply a contiguity filter to grow out land use from time 2 to a later time period. In essence, the CA will develop a spatially explicit weighting more heavily areas that proximate to existing land uses. This will ensure that land use change occurs proximate to existing like land use classes, and not wholly random. Overlay operations, which is the last method of the three, identifies the actual location and magnitude of change, although this was limited to the built-up land. Boolean logic was applied to the result through the reclass module of A9AYTZ355N, which assisted in mapping out separately areas of change for which magnitude was later calculated for. The land consumption rate and absorption coefficient formula are given below. LCR equals APA equals areal extent of the city in hectares, P equals population, LAC equals A2, A1 P2, P1 A1 and A2 are the areal extents, in hectares, for the early and later years, and P1 and P2 are population figure for the early and later years respectively. Yates and Garner, 1976. LCR equals a measure of compactness which indicates a progressive spatial expansion of a city. LAC equals a measure of change in consumption of new urban land by each unit increase in urban population. Both the 2001 and 2015 population figures were estimated from the 1991 and the estimated 2001 population figures of Ilorin respectively using the recommended National Population Commission, NPC, 2.1% growth rate as obtained from the 1963/1991 censuses. The first task to estimating the population figures was to multiply the growth rate by the census figures of Ilorin in both years, 1991, 2001, while subsequently dividing same by 100. The result was then multiplied by the number of years being projected for, the result of which was then added to the base year population, 1991, 2001. This is represented in the formula below. N equals R/100 PO, 1. Pn equals PO plus, NT, 2, Pn equals estimated population, 2001, 2015, PO equals base year population, 1991 and 2001 population figure, R equals growth rate, 2.1% and equals annual population growth. T equals number of years. Projecting for the formula given for the population estimate was developed by the researcher in evaluating the socio-economic implications of change. The effect of observed changes in the land use and land cover between 1972 and 2001 were used as major criteria. Chapter 4 Data Analysis 4.0 Introduction. The objective of this study forms the basis of all the analysis carried out in this chapter. The results are presented in form of maps, charts and statistical tables. They include the static, change and projected land use land cover of each class. 4.1 Land use land cover distribution. The static land use land cover distribution for each study year is derived from the maps are presented in the table below. Farmland 2,437.6272325 7,965.57338 14,068.4949 Wasteland 41,436.771 43 55,561.14959 50,317.26352 built up land 2,198.27342 9,702.8136 10,815.921 11 forest land 11,036.494 12 21,393.0405 22 19,960.2315 21 water body 16,874.6562 18 1,326.8916 787.5576 1 total 95,949.468 195,949.468 195,949.468 100 Table 4.1 Land Use Land Cover Distribution, 1972, 1986, 2001. The figures presented in Table 4.1 above represents the static area of each land use land cover category. For each study year, built up in 1972 occupies the least class with just 2% of the total classes. This may not be unconnected to the fact that the town, Ilorin, was made the state capital in MAPI derived from Landsat image of Ilorin in 1972-1967 which is just 5 years old from the date of creation to the date the image was taken. Also, farming seems to be practiced moderately, occupying 25% of the total classes. This may be due to the fact that the city is just moving away from the rather traditional setting where farming seems to form the basis for living. Apart from this, the time of the year in which the area was imaged which happens to fall within the onset of Harmattan could also be a major contributing factor to the observed classification, contributing to the high percentage of wasteland and the low percentage of forest land. Water body also seems to be arbitrarily exaggerated in the classification due to the aforementioned problem in Section 3.5 in 1986. Wasteland still occupies the highest class with 59% of the total class, taking up more than half of the total classes. Furthermore, the high percentage may be due to the season of the year as mentioned in the last paragraph. Water body takes up the least percentage in the total class. The pattern of land use land cover distribution in 2001 also follows the pattern in 1986. Wasteland still occupies a major part of the total land but there exists an increase by half in the total farmland. Still, water body maintains the least position in the classes whilst built up occupies 11% of the total class. 4.2 Land consumption rate and absorption coefficient 1972 0.005 1972/86 0.09 1986 0.02 86/2001 0.005 2001 0.01 Table 4.2.1 1977 400,000 EPLA in Group 1977 1984 480,000 Oregon 1986 2001 689,700 Researchers Estimate Table 4.2.2 Population Figure of Ilorin in 1977, 1984 and 2001. It should be noted here that the closest year population available to each study year as shown above were used in generating both the land consumption rates and the land absorption coefficients as given in Table 4.2.1 4.3 Land use land cover change, trend, rate and magnitude farmland minus 16,410.699-17 6,102.9216 14,068.4949 1.05 Wasteland 14,124.3777 16-5,243,886-7 50,317.263 1.05 Built up land 7,504.5402 1,113.1074 10,815.9210 0.15 Forest land 4,518.3838 10 1,432.809-1 19,960.2315-0.15 Water body 16,874.6562-17-539.3340 787.55760 Table 4.3 Land use land cover change of Ilorin and it environs, 1972, 1986 and 2001 From Table 4.3, there seems to be a negative change, that is, a reduction in farmland between 1972 and 1986. This may not be unconnected to the change in the economic base of the city from farming to other white-collar jobs as a result of the creation of Kwara State in 1967, in which Ilorin was made the state capital. Subsequently, built-up land increased by 8%, while both forest land and wasteland both increased by 10% and 16% respectively. Many projects were embarked on after the creation of Kwara State, which also falls within the oil boom era of the 1970s, and this attracted a lot of people to the area, thus contributing to the physical expansion of the city, as evident in the increased land consumption rate from 0.005 to 0.02 and land absorption coefficient by 0.09 between 1972 and 1986. Many of these projects include the Army Barracks at Sobi, Adual Housing Estate, the International Airport, Niger River Basin Authority Headquarters, University of Ilorin, among many others, which all encouraged migration into the city. The period between 1986 and 2001 witnessed a drop in the rate at which the physical expansion of the city was going as against 1972 and 1986. For instance, the built-up land only increased by 1% as against the 8% increase between 1972 and 1986. This is also evident in the drop observed in the land absorption coefficient from 0.09 between 1972 and 1986. Indeed, the austerity measure known as SAP, introduced into the country at this period to restore the country's economy, could be a major factor to what was witnessed at this period. Also, there was a general increase of 7% in farmland, which is evident in the 7% reduction of wasteland and 1% reduction of forest land. This may be as a result of the shift back towards farming after the initial excitement of the oil boom, which attracted many people from farming to white-collar jobs. Furthermore, water body seems to remain at 1%, though there are slight differences in the total hectare between this period. This was not so in 1972 because Asa River was not yet dammed, which was the case in the period between 1986 and 2001 as shown in the maps. MAP 2. Derived from Landsat image of Ilorin in 1986 4.4 Nature and location of change in land use land cover. An important aspect of change detection is to determine what is actually changing to what, that is, which land use class is changing to the other. This information will reveal both the desirable and undesirable changes and classes that are relatively stable over time. This information will also serve as a vital tool in management decisions. This process involves a pixel-to-pixel comparison of the study or images through overlay. In terms of location of change, the emphasis is on built-up land. Map 4 shows this change between 1972 and 1986. The observation here is that there seemed to exist a growth away from the city center following the concentric theory of city growth postulated by Christler, 1933. Although the pattern seems to be uniform, there exists more growth. MAP3. Derived from Landsat image of Ilorin in 2001 towards the southwestern part of the city, comprising of the Asadam area, Adual Estate and Airport. Between 1986 and 2001 as shown in Map V, there exist drastic reductions in the spatial expansion of the city. The only noticeable growths are on the edges of the developed areas of 1986 built-up land. For the projected change as shown in Map 6, the edges of built-up land seems to have been filled up with developments by 2001, leaving the only noticeable developments to areas around the city center. These therefore suggest that there might be a high level of compactness in Ilorin by 2015. On the other hand, looking at the nature of change under stability, that is, areas with no change and instability, loss or gain by each class between 1972 and 1986, particularly in the change in hectares as observable in Table 4.1. Stability seems to be a relative term, as no class is actually stable during this period except one observed from the percentage change. Thus, between 1972 and 1986, farmland has a loss of 17% but gained by 7% between 1986 and 2001. Wasteland, on the other hand, gained by 16% between 1972 and 1986 but lost by 7% between 1986 and 2001. Built-up land increased, that is, gained by 8% between 1972 and 1986, which is incomparable with the reduced increase of 1% between 1986 and 2001. Forest land gained by 10% between 1972 and 1986 but lost by 1% between 1986 and 2001, while water body being arbitrarily exaggerated in 1972 could not be compared with 1986, but there exists a relative stability in this class between 1986 and 2001 as evident in the 0% increase shown in the table. MAP4 derived from the overlay of 1972 and 1986 land use land cover map. MAPV derived from the overlay of 1986 and 2001 land use land cover map. 4.5 Transition probability matrix. The transition probability matrix records the probability that each land cover category will change to the other category. This matrix is produced by the multiplication of each column in the transition probability matrix by the number of cells of corresponding land use in the later image. For the 5x5 matrix table presented below, the rows represent the older land cover categories and the column represents the newer categories. Although this matrix can be used as a direct input for specification of the prior probabilities in maximum likelihood classification of the remotely sensed imagery, it was however used in predicting land use land cover of 2015. 0.1495, 0.5553, 0.0885, 0.1969, 0.0097, 0.1385, 0.5132, 0.1735, 0.1692, 0.0057, 0.0471, 0.3902, 0.5029, 0.0507, 0.0090, 0.2163. 0.4050, 0.0501, 0.3203, 0.0083, 0.1682, 0.4378, 0.0633, 0.3174, 0.0133. Table 4.5 Transitional probability table derived from the land use land cover map of 1986 and 2001. Row categories represent land use land cover classes in 2001 whilst column categories represent 2015 classes. As seen from the table, farmland has a 0.1495 probability of remaining farmland and a 0.5553 of changing to wasteland in 2015. This therefore shows an undesirable change, reduction, with a probability of change which is much higher than stability. Wasteland during this period will likely maintain its position as the highest class with a 0.5132 probability of remaining wasteland in 2015. Built upland also has a probability as high as 0.5029 to remain as built upland in 2015, which signifies stability. On the other hand, the 0.4050 probability of change from forestland to wasteland shows that there might likely be a high level of instability in forestland during this period. Water body, which is the last class, has a 0.0133 probability of remaining as water body and a 0.4378 probability of changing to wasteland, which may not however be a true projection of this class except there is an occurrence of drought in the region. 4.6 Land use land cover projection for 2015: 16,583.5458, 47,432.475, 11,026.456, 20,397.871, 509.118, 1750, 1121. 1 Table 4.6 Projected land use land cover for 2015. The table above shows the statistic of land use land cover projection for 2015. Comparing the percentage representations of this table and that of Table 4.1, there exist similarities in the observed distribution, particularly in 2001. This may tend to suggest no change in the classes between 2001 and 2015, but a careful look at the area in hectares between these two tables shows a change, though meager. Thus in Table 4.6, wasteland still maintains the highest position in the class whilst water body retains its least position. Forestland takes up the next position, followed by built upland and finally, farmland. As seen in Map 6, there is likely to be compactness in Aloran by 2015, which signifies crowdedness. MAP6 derived from the 1986 and 2001 land use land cover map. MAP7 derived from the overlay of 2001 and 2015 land use land cover map. Chapter 5.1 Findings, Implications and Recommendations. There is likely going to be crowdedness brought by compactness in Aloran come 2015. This situation will have negative implications in the area because of the associated problems of crowdedness like crime and easy spread of diseases. It is therefore suggested that encouragement should be given to people to build towards the outskirts through the provision of incentives and forces of attraction that are available at the city center in these areas. Oh indeed, between the period of 1986 and 2001, there has been a reduction in the spatial expansion of Ilorin compared to the period between 1972 and 1986. There is a possibility of continual reduction in this state over the next 14 years. This may therefore suggest that the city has reduced in producing functions that attracted migration into the area. Indeed, there have been many defunct industries within this period. It is therefore suggested here that Kwara state government should encourage investors both local and foreign and more importantly, see how the defunct industries will come up again. After the initial reduction in farmland between 1972 and 1986, the city has witnessed a steady growth in this class and indeed, may continue in this trend in 2001-2015. For this projection to be realistic, it's suggested here that a deliberate attempt should be made by the state government to achieve this since this will lead to food security and more importantly, it will be a source of revenue to the state. A wasteland seems to be reducing between 1986 and 2001 and between 2001 and 2015 thus signifying a desirable change. Forest land has been steady in reduction between 1986 and 2001 and indeed, this may likely be the trend 2001-2015. It will be in the good of the state and indeed, the nation as a whole if the moderate reduction in forest land observed in between 1986 and 2001 which is also projected by 2015 is upheld. Land consumption rate which is a measure of compactness which indicates a progressive spatial expansion of a city was high in 1972-86 but dropped between 1986 and 2001 and this drop is also anticipated before 2015. Also, land absorption coefficient being a measure of consumption of new urban land by each unit increase in urban population which was high between 1972 and 1986, reduced between 1986 and 2001. This therefore suggests that the rate at which new lands are acquired for development is low. This may also be the trend in 2001-2015 as there seems to be concentration of development at the city center rather than expanding towards the outskirts. This may be as a result of people's reluctance to move away from the center of activities to the outskirts of the city. 5.2 Summary and Conclusion. This research work demonstrates the ability of GIS and remote sensing in capturing spatial temporal data. Attempt was made to capture as accurate as possible 5 land-use land cover classes as they change through time. Except for the inability to accurately map out water body in 1972 due to the aforementioned limitation, the 5 classes were distinctly produced for each study year but with more emphasis on built-up land as it is a combination of anthropogenic activities that make up this class. And indeed, it is one that affects the other classes. In achieving this, land consumption rate and land absorption coefficient were introduced into the research work. An attempt was also made at generating a formula for estimating population growth using the recommended National Population Commission 2.1% growth rate. However, the result of the work shows a rapid growth in built-up land between 1972 and 1986 while the periods between 1986 and 2001 witnessed a reduction in this class. It was also observed that change by 2015 may likely follow the trend in 1986 Albanian lex and 2001 Albanian lex things being equal. References: A9AYTZ355N and A9AYTZ355N. 1999, Land-use land cover change evaluation in Sokoto, Rima Basin of northwestern Nigeria based on Archival of the Environment, AARSE. Ongoing Information Technology Applications for Resource and Environmental Management in Africa. Pages 143 to 172. Arvind C. Pandey and M.S. Nathawit 2006. Land-use land cover mapping through digital image processing of satellite data, a case study from Panchkula, Ambala and Yamunanagar districts, Haryana State, India. Anderson, et al. 1976. A land-use and land cover classification system for us with remote sensor data. Geological Survey Professional Paper number 964, U.S. Government Printing Office, Washington, D.C. pages 28. Christler, 1933, Central Place Theory, Wikipedia Free Encyclopedia Koppen, P. and Bauer, M. 1996. Digital Change Detection in Forest Ecosystems with Remote Sensing Imagery. Remote Sensing Reviews. Volume 13. Pages 207 to 234. Daniel, et al., 2002. A comparison of land use and land cover change detection methods. ASPRSACSM Annual Conference and FIGXXII Congress PG2. Dimiotti, et al. 1995. An analysis of land use land cover change using the combination of MSS Landsat and Land Use Map. A case study of Yogyakarta, Indonesia, International Journal of Remote Sensing 17, 5, 931-944. ERDAS, Incorporated 1992. ERDAS Production Services Map State for Georgia DNR in the Monitor, Volume 4, Number 1, ERDAS, Incorporated, Atlanta, Georgia. EOSAT 1992. Landsat TM Classification International Georgia Wetlands and EOSAT Data User Notes, Volume 7, Number 1, EOSAT Company, Lanham, Maryland. EOSAT 1994. EOSAT, a statewide purchase plan keeps South Carolina residents in the know, in EOSAT Notes, Volume 9, Number 1, EOSAT Company, Lanham, Maryland. ERDAS Field Guide. 1999. Earth Resources Data Analysis System. ERDAS Incorporated. Atlanta, Georgia. Pages 628. Fitzpatrick Linz et al., 1987. Producing Alaska Interim Land Cover Maps from Landsat Digital and Ancillary Data, in Proceedings of the 11th Annual William T. Pecor Memorial Symposium, Satellite Land Remote Sensing, Current Programs and a Look into the Future. American Society of Photogrammetry and Remote Sensing, pages 339 to 347. Idrisi 32 Guide to GIS and Image Processing, Volume 1, Release 2. Pages 17. Kwara State of Nigeria, 1997, Kwara State Diary, Government Press. Ilorin. McLeod and Connelton. 1998. A quantitative comparison of change detection algorithms for monitoring eelgrass from remotely sensed data. Photogrammetric Engineering and Remote Sensing. Volume 64. Number 3. Pages 207 to 216. Meyer, W.B. 1995. Past and Present Land Use and Land Cover in the USA Consequences. Pages 24 to 33. Moshin A., 1999. Environmental Land Use Change Detection and Assessment Using with Multi-Temporal Satellite Imagery. Zhejiang University. Oliniran, J.O., 2002. Rainfall Anomalies in Nigeria, The Contemporary Understanding 55th Inaugural Lecture, University Press. Ilorin. Olaronfemi J.F., 1983. Monitoring Urban Land Use in Developed Countries, An Aerial Photographic Approach, Environmental in 9, 27-32. Oyebanji, J.O. 1993, Kwara State Enudo, R.K. and Mammon, A.D., eds., Nigeria, Giant in the Tropics, Volume 2, State Survey, Gabumo Publishing Company Limited. Logos. Oyegun, R.O., 1983. Water Resources in Kwara State. Matami and Sons Printing and Publishing Co. Limited. Ilorin. Oyegun, R.O., 1985. The Use and Waste of Water in a Third World City Geo-Journal, Riddle Publishing Company, 10.2, 205-210. Reepsame, W.E., Meyer, W.B., and Turner, B.L. 2. 1994. Modeling Land Use and Cover as Part of Global Environmental Change. Climate Change. Volume 28. Pages 45. Shoshani, M., et al., 1994. Monitoring Temporal Vegetation Cover Changes in Mediterranean and Arid Ecosystems Using a Remote Sensing Technique, Case Study of the Judean Mountain and the Judean Desert. Journal of Arid Environments, 33, 9-21. Singh, A. 1989. Digital Change Detection Techniques Using Remotely Sensed Data. International Journal of Remote Sensing. Volume 10, Number 6, pages 989 to 1003. U.S. Geological Survey, 1999. The Landsat Satellite System link, USGS on the World Wide Web. URL, http://landsat7.usgs.gov/ landsat_sat.html. November 10, 99. University of Ilorin, Department of Geography. 1981, Ilorin Atlas. Ilorin University Press. Welke, D.S., and Finn, J.T. 1996. Remote Sensing Imagery for Natural Resources Monitoring. Columbia University Press, New York. Pages 295. A9AYTZ355N and Ranking LQY, 1999. Change detection based on remote sensing information model and its application to coastal line of Yellow River Delta, Earth Observation Center, NASA, China. Yates, M. and Garner, B. 1976. The North American City, Harper and Row Pub. New York. Figure I, Land Use Land Cover Categories of Ilorin in 1972. Figure 2, Land Use Land Cover Categories of Ilorin in 1986. Figure 3, Land Use Land Cover Categories of Ilorin in 2001. Figure 4, Land Use Land Cover Categories of Ilorin in 2015-20. Thank you for taking your time to listen to me. I hope you enjoyed learning about 3.2 data acquired and source change detection in land use and land cover using remote sensing data and GIS as much as I did. Kindly remember that you can get a custom, plagiarism-free essay at OWL Essays for as little as $10. The link is in the description. See you next time.